Welcome to the first of the academic year 2023 to 2024 discussion hour series. For those that don't know me, my name is Michaela Pasquale. I'm a second year PhD student here, and I'll be organizing the series for this academic year. So if you have any questions, comments, qualms, queries, please don't hesitate to reach out and get in contact with me. I'm really excited to start this series off with Dr. Ian Dalziel. For those that are not familiar with Ian, he was born in Scotland and received both his bachelor's and doctoral degrees from the University of Edinburgh. Right after that, he was an assistant professor at Wisconsin-Madison for some years, and then migrated to Columbia University to finally make his way over here as a research scientist at the Institute for Geophysics, and also a professor for the now new Earth and Planetary department. I know I should have corrected that in my email, but the EAPS department now. For research interests, he specializes in tectonic studies in the Scottish Highlands, Canadian Shield, the Andes, Southern Africa, Falkland Islands, Scotia, Arc, Antarctica, and the Southern Ocean. So anywhere that you can probably think of. And something that was not included in this brief CV that he sent to me is that he recently received a very high British honor of the Polar Medal, which he'll be going to England in October to celebrate with the King. So with that, I'm very excited to hear about his research presentation today. So please help me welcome him.
Well, the King may be busy. You might pass it on to Prince of Wales or something like that.
Even better.
Thank you. Well, thanks for coming, everybody, in person and online. I offered this as a talk as a backup for us in case anything cancelled during the academic year or Michaela had a slot she couldn't fill. I didn't expect to be giving the first talk. When she came back and indicated the first one was still open, I thought, oh, she's going to stick me in there, and she did. So here we go. I'm going to talk about the paleogeography of the supercontinent Rodinia, which existed approximately from 1 billion years to about 750 million. And I'm going to particularly talk about the geology and suggest that Laurentia may be the geological key. And I use that in quotes because, as you see in the bottom left there, and you may recall, Alex Dutoit in his classic book, Our Wandering Continents in 1937, which, by the way, was the year that I was born. You can do the math. He referred to Africa as the key to Pangaea. And so I'm suggesting that Laurentia may be the key to Rodinia. And the main reason being that, as we'll come to later on, that Laurentia, the ancient core of the North American continent, is surrounded by late Precambrian to earliest Paleozoic rifted margins. It broke out from within something. And that is what we're going to explore. Oops. Okay. I need to give acknowledgement here to my good friend, the late Elridge Moores, because this story started really gained traction, at least in 1991, after a field trip that I ran to the Antarctic, to the Scotia Arc, for the International Geological Congress, which was based in Washington, D.C. in 1989. And I was able to talk the National Science Foundation out of a small ship for 3 weeks to take a bunch of people, of eminent geologists who'd never been to Antarctica before. The idea was to kind of pull Antarctica a little more into the mainstream of global geology. And I think we tended to do that in unexpected ways. Elridge published after that cruise a paper in geology in May of 1991, which he called the Southwest US East Antarctica or SWET hypothesis, suggesting that East Antarctica, in the bottom left here, may have been juxtaposed with the Southwest US before the opening of the Pacific Ocean. And so the intention here is to sort of revisit this SWET hypothesis 30 years on. It's still a work in progress. And basically what I'm going to do is to give you a very broad outline of what of ideas about the paleogeography of Rodinia that have developed over that period of time. To go back to talking about the criteria that were used to argue for a Pangea before we understood seafloor spreading. And then to go on to consider Laurentia as a potential geological key to Rodinia. You might bear in mind, those of you who were not born in 1937, that one of the arguments that was always, or one of the questions that was raised when people were talking about continental drift and the possible existence of a Pangea back in geological time was Pangea, if it existed, was it the original configuration of continents on the planet? Or had there been some other configurations before that? That was something that had been considered back at the time before we understood seafloor spreading and plate tectonics. The map that Eldridge Moores came up with in his early paper in 1991, showing the Southwest US against East Antarctica, we had discussed in the course of that field trip to the Scotia Arc region and the Antarctic Peninsula. We didn't actually get to the rifted margin of East Antarctica on that trip. We were more on the subducting Phanerozoic Pacific margin. But we did discuss the origin of the margin. And he went back and found papers and abstracts by Eisbacher and Bell and Jefferson, Canadian geologists, comparing the Neoproterozoic stratigraphy of the Southwest Canada with that of Southeast Australia. And with his antennae poked up for Antarctica, having been just come back from there, he said, well, that must have meant that if Southwest Canada was against Southeast Australia, that must have meant that East Antarctica was against the Southwestern US. And that was the origin of its brainwave, so to speak, that led to its suggestion of the SWET hypothesis for the world before the opening of the Pacific Ocean. I followed through using the plates system in here at UTIG with the reconstruction in the middle there, top center, which suggested that, in fact, Laurentia might have been sandwiched between East Antarctica, Australia on one side, and West Gondwana, in other words, Africa, South America, on the other side. Paul Hoffman, who heard about all this going on, had a more sophisticated version of my sort of Laurentia-centric reconstruction, breaking out the cratons of Gondwanaland, particularly as separate entities. And a point that I'll come back to later on, how do you have to fit this in space and time as well as in space. And so I had asked myself the question in my paper, okay, so how did we then get from a Rodinia in the Neoproterozoic to what we know was Pangea at the end, by the end of the Paleozoic, and demonstrated that using the paleomagnetic data, it was possible that Laurentia might have made what one of my former graduate students referred to it as an end run around the Paleo-Andean margin, Proto-Andean margin of Gondwanaland of South America, particularly during the Paleozoic, to reach its position within Pangaea that we know that it had before the opening of the Mesozoic ocean basins. In the meantime, many intervening years, many reconstructions have been proposed, alternate ones. Karl Karlstrom and his colleagues came up with what they called Aus-Bus for Australia against Southwest US. And Wingate and his colleagues in Western Australia suggested Aus-Mex, based on paleomagnetic data, with Mexico against Australia. These two reconstructions suffered from leaving thousands of kilometers of unexplained rifted margin in either Laurentia or East Antarctica or both. And that didn't satisfy me because I was looking for large fragments that may have rifted from each other, thousands of kilometers long. I didn't like the idea of leaving unexplained, at the time at least that they wrote the papers, thousands of kilometers of late Precambrian rifted margin. Lee and others, and again in Western Australia, suggested that there may have been a missing link of the South China block between Laurentia and East Antarctica, Australia, although that has largely been disproved on paleomagnetic grounds in the intervening years. David Evans in Yale had a separate story based on he called it a radically revised Rodinia, based purely on paleomagnetic data, not on any geology at all, and at completely different positions than anything that resembled East Antarctica, Australia on the one hand against Western Laurentia on the other. I modified the reconstruction that I'd come up with in 1991 by suggesting that the Arica embayment in the South American margin might have matched the Appalachian, Caledonian, or Scottish promontory of Laurentia. And that suggested also the former existence of what I call the Texas Plateau, for reasons I'll come up with later on. I still think that probably existed, although maybe in a slightly less macho form than it's shown in this reconstruction. But again, we're looking here at the suggestion of a Laurentia-centric entity. Very recent, or much more recent reconstructions and a series of reconstructions from deep in Precambrian time through to Rodinia and Pangaea by Meredith and others, Evans, based mainly on paleomagnetism, and Johansson, based on largely on geochronologic and geochemical data from the Grenvillian belts, you'll see have also come up with largely Laurentia-centric reconstructions. These are based to considerable extent, except for Johansson, which is geochemical, geochronological, but Evans and Meredith are very strongly based on paleomagnetism. But as many of you, most of you will appreciate, paleomagnetism further back in time gets very complicated because of the increased amount of time you have for overprints, thermal overprints. And it gets difficult, was just more complicated to use. But the real basis, as I indicated at the very beginning, for a Laurentia-centric entity having existed in the late Precambrian is the fact that, as shown by Paul Hoffman in his classic map of the rifting between 8.8 and 0.6 gigayears, showing the rifted margins, about 14,000 kilometers of rifted margin around the Laurentian continent. And an update of that by MacDonald and others merely refines the timing of the different rift segments of the around the Laurentian margin. Let's take a look at how Pangaea was reassembled before seafloor spreading became understood. Dutoit's map in 1937, you'll notice, is essentially the same as that of Norton and Slater in 1979, which was one of the first ones to be based on seafloor spreading data. Very little difference between the two. And we'll come back to the basis of Dutoit's reconstruction later on. A very important part of that was the reconstruction of what he referred to as the Samfrau geosyncline for South America, Africa, Australia, the neurogenic belt, which extended, as we know it did nowadays, from South America through to Australia. So we had something right. Continental outlines were used. It seemed that the way back in the even into almost medieval times, the match between the Horn of Brazil and the Gulf of Guinea in Africa were recognized and oohed and ahed about whether they were related in some way originally. And the quantitative aspect of this was put forward by Edward Bullard, Everett and Smith in the late 60s, when they did a computer fit of the continents bordering the Atlantic, showing minor overlaps in the case, for instance, of the Niger Delta with Brazil, and underlaps, for instance, gaps where South America didn't quite fit with the Falkland Plateau. But nonetheless, a very compelling fit at the 500 meter submarine contour, not at the continental margins. And about the same time, Patrick Hurley in MIT and his colleagues in Brazil compared the geochronology, which was emerging at the time, of the Brazilian shield with West Africa. And they matched the geological age provinces very impressively of the two continents. And Hurley went so far as to call this the confirmation of continental drift. The fact that not only did the continental margins fit, but the geology fit was really, really critical. And it's always been interesting to me that different people had different ideas of what finally confirmed continental drift. For Hurley, it was the geochronology. For paleontologists, it was the finding of Lystrosaurus, the non-marine tetrapod in Antarctica, as well as the other southern continents. Different people had their final clinching evidence, often because it was in their field, I think. In my view, what really confirmed the final nail in the coffin, so to speak, or a bunch of nails, because they were drill holes drilled by our former director here, Art Maxwell, and his colleagues on a deep sea drilling leg 3, actually, from Dakar in West Africa to Rio de Janeiro. They pogo sticked their way across the Atlantic and demonstrated conclusively that the ocean basins got older away from the mid-Atlantic ridge. And the oldest parts were adjacent to the continents. That transferred the evidence to the ocean floors. There we go. Another line of evidence that was used were so-called piercing, what John Kroll, when looking at San Andreas Fault and had points and lines that had been displaced along the San Andreas, he called piercing points, and translating that into the scale of continents and supercontinents. Holmes, for example, showed, following Wegener, indeed, and Bailey and Dutoit, that the Caledonian mountain chain and the Hercynian mountain chain seem to have their counterparts and be crossing as they reach the Atlantic margins on either side. And Dutoit, as I mentioned before, notably traced the Sierra de la Ventana in origin in southern Buenos Aires province of Argentina into a Cape Fold belt of his native Africa, and in a real masterpiece of geological prediction, in my view, predicted that this origin would continue through a piece of Antarctica that hadn't even been discovered yet at the time, through to the Hunter Bowen origin of Eastern Australia. And so these piercing points provide very strong evidence for the former juxtaposition of the different segments of origins. However, until we knew about the ocean floors, it was always possible that we had segments of the origins had sunk beneath an ocean basin that was flowed by a continent. Until we really knew about the ocean basins, that was always, it seems to be, a possibility. Another line of evidence that was used and could be used were what I called in 1993 tectonic tracers, like geochemical tracers for ocean water. Most notable is probably the northwest foreland, Caledonian foreland of Scotland, which we knew since Salter's work in 1859 had a strictly Laurentian fauna to it, benthic fauna. And that was followed up by Bailey, by others, and Peach and Horn and others in 1907, who compared the lithology as well as the fauna, and said this looked as if it had been part of a province of North America. But they, again, not knowing about the ocean basins, and don't understand why. But in fact, the Northwest Caledonian foreland, on the opposite side, the Avalon platform of southeastern Newfoundland with its European fauna, and other, what I would call tectonic tracers now, the Grunahonya terrain of Antarctica, which is part of the Kalahari Craton, and some recent work which Josh Malone, Brian, and myself did, showing that it's likely that the Falkland Islands, as suggested by Ray Adey, or the Lithonian microplate, as it's called, might have been off southeastern Africa originally, and now finished up in the Falkland Plateau of South America. And then there's the Terra Adélie of East Antarctica, which correlates with the Gawler Craton of Australia. All of these seem to be little calling cards saying, in the case of the Northwest Caledonian foreland, for example, hey, North America was here once. The Grunahonya and Antarctica saying Kalahari was here once. And so this is a line of evidence that could be used to try to understand Rodinia, which existed, of course, before any existing seafloor today. So we don't have that seafloor to guide us in the way that eventually we did for Pangaea. Another line of evidence are large igneous provinces. Camp, the Central Atlantic magmatic province, at about 200 million years, with fragments in both of the Americas, Africa, and Europe. The Karoo-Ferrar of Africa, Antarctica, and over to Tasmania, at 182 million years. And the North Atlantic Igneous Province at 55 to 50 million years ago. It's 60 to 55, which is Larry Lover now recently suggested that the dikes in the northwest of Britain, the British Isles, might have correlated with a time when the Iceland hotspot was in West Greenland. But this large igneous province has been known for a long, long time to have existed at about the same age in Western Europe, Greenland, and over into the Baffin Bay area of Canada. So large igneous provinces are another line of evidence. So let's think about Rodinia with using these these lines of evidence. The craton outlines. I've already suggested that it is significant probably to think of in terms of needing to match major rifted margins with each other in terms of length. And then there are significant aberrations in the margins. For instance, in southwestern US, the Mojave province, although it's rather exaggerated in maps using modern geography for the extent of the Mojave province, perhaps making it rather more of a promontory than it really should have been because of the Mesozoic, Cenozoic distortion that's gone on. But nonetheless, that seems to be a promontory in the western margin of present-day Laurentia. And the eastern margin, when you restore Greenland against Labrador, you're left with this very obvious Caledonian Appalachian promontory, which being a Scot, I often refer to as the Scottish promontory, because little Scotland was sticking out there right at the tip of that. And it's tempting to think that those, although perhaps not quite so prominent as the Brazil to Gulf of Guinea for Pangaea, might have some significance in reconstructing Rodinia. Burt and Berry and Karlstrom had suggested earlier on, back in the late 90s into 2001, that in fact the Mojave promontory might fit into an embayment in the Tasman line, the eastern margin of the Australian cratons in southeastern Australia. But as I've mentioned before, this leaves you with thousands of kilometers, 3,000 to 4,000 kilometers of the Antarctic margin unexplained. And recent alternative to that has appeared in the geophysical data from East Antarctica. In the top left there, you see the location of the main map, which shows an embayment in the area, whether I can, no? I don't seem to be able to find a pointer here without. Okay, now we can. Nope. Don't seem to be able to do that. Anyway, in the area of the Pensacola Mountains, there seems to be an embayment in the East Antarctic craton, which matches rather closely as I admitted, the part of the possibly slightly exaggerated Mojave promontory of Western Laurentia. And one of the things, matching those two allows the juxtaposition of two very singular ore deposits in the Olympic Dam of southeastern Australia and the Wernicke breccias of the Yukon, which Thorkelson and others had pointed out were at the same paleolatitude at the inception at about 1.6 billion years. And reconstruction would juxtapose them. However, the strongest line of evidence for the correlation of the Laurentian craton with East Antarctica comes from the work of John Gooch, Mark Fanning, and their colleagues, particularly being able to find in the moraines of the Transantarctic Mountains, the 1.4 or 1.5 billion year old apparent equivalents in every respect that they could find: geochronological, geochemical, isotopes, everything, with the granite rhyolite province of Laurentia. That is probably the strongest single piece of evidence, I believe, that there is to correlate the Laurentian craton with the East Antarctic craton. You remember that when you're dealing with the Pacific margin of Laurentia, we're talking of a margin that is not marked by a suture. I contrast that with the Appalachian Caledonian side, where the late Precambrian, early Paleozoic rifted margin followed an old suture, the Grenvillian age suture. Where there's a suture that's being followed, you don't necessarily expect to be able to correlate across that suture, because there's nothing that says that before Grenvillian times, South America, for example, and Laurentia had to be together. Whereas if there's no suture at the rifted margin, you do expect to be able to correlate with the juxtaposed margin. The difficulty that I have, and John George and I have discussed this at great length, difficulty that I have in reconciling the excellent evidence, as I said, for the correlation of the clasts in the moraines of the Transantarctic Mountains with the granite rhyolite province, is that it leads the Grenville province in green there, coming into the Transantarctic Mountains in a place where there are a few detrital Grenvillian zircons, but not much other evidence for that. And I find it very difficult to believe that the Grenville belt, which is so well developed in eastern North America and down here into the southwestern, into Texas and West Texas, just more or less disappears at that margin. So that is in contrast to putting the Mojave Block into the embayment near the Pensacola Mountains further south in Antarctica. Talking of piercing points and origins, that is where Elridge Moores particularly suggested that the Yavapai Mazatzal of southwestern US might continue into the Shackleton Range in Antarctica. That is backed up by, to some extent, by the geochemistry of the igneous rocks and metamorphosed igneous rocks in the Shackleton Range and the Yavapai Mazatzal, by the geochemistry, but it is not quite as firm as I would like it to be. There are similarities, and it's worth pursuing that even further, I believe. The place where the Grenville might continue, and I'll talk about that in more detail later, is into the eastern part of the Weddell Sea, into what's called the Maud Belt, between the Grunahonya terrain, the bit of Kalahari, and Coates Land in what's called the Maud Belt, which is Grenvillian origin, Grenvillian age, 1 billion years or so. And in fact, in quite a lot of detail, there are similarities between the Grenvillian of eastern US and Canada and the Maud Belt of Antarctica. So piercing points can be used. Matching cratons, as I mentioned, across a suture, for instance, the eastern margin of Laurentia, the Appalachian Caledonian belt. Paul Hoffman and I both suggested that the match between the Grenvillian rocks of eastern North America and the Sunzas belt of western Amazonia might suggest that they were juxtaposed. And Johansen and his colleagues found similarities, close similarities between the Grenvillian and Sunzas belt in terms of age, and support such a reconstruction. Getting into a little more detail, once you get into lead isotopes, as Mocher, I may be mispronouncing that, and his colleagues suggested, we point out that the southern part of the Appalachians and the Mars Hill terrain has a very similar lead isotope composition to Amazonia. And so this is getting into rather more detail than just saying it's geochronology. And it's there's a boundary in Laurentia between the southern Appalachians and, for example, the northern Appalachians basement and the Adirondacks in their geochemical characteristics in the isotope composition. And so this is a slightly firmer basis for saying not only that there you have Grenvillian age rocks on either side, but you have some isotope geochemistry backing up correlation between the southern Appalachians and the southern part of the southwestern part of Amazonia. Tectonic tracers were another line of evidence that we were discussing for Pangaea before we understood the seafloor. And one particular place that's come to our attention is Coates Land at the head of the Weddell Sea in the southern part of the map there. Joining Maudland in the north with the Grunahonya block as part of Kalahari, the Maud origin of Grenvillian age in between. But Coates Land has some very interesting aspects, even if it is only exposed in 3 little nunataks. At the very head of the Weddell Sea, a place called Vassal Bay. There are the Littlewood nunataks, L there, the Bertrab B, where the Argentines have a base, Belgrano dos. And there we are collecting some samples for paleomagnetism from the Littlewood nunataks. And then on a cliff beneath an ice fall, there are the Moltke nunataks. Well, we went there with a fixed wing aircraft. There was no way we were going to land there. Some intrepid Indian colleagues, after following our work there, you can see in the bottom left picture there, a helicopter. They got themselves lowered by a helicopter underneath the icefall and collected some rocks. And whereas the Littlewood and Bertrab up on top are flat lying, pretty well undeformed granophyres and rhyolites, the Moltke nunataks are highly deformed, apparently low-grade metamorphics, which we have samples of, courtesy of our Indian colleagues. And my colleague Stacey Lowy in the department has started work on those. We're hoping to get some more results. I'll show you some preliminary ones. But the interesting things about the rhyolites and granophyres of the Bertrab and Littlewood nunataks up on top of the ice, just poking up above the ice, are that they have exactly the same lead isotopes as the Keweenawen of North America. They're the same age at 1.1 billion years as both the Mkondo of Africa, which of course is much closer, in present day and in Gondwana reconstructions than the Keweenaw of North America. But the isotopes are very decidedly Laurentian, Keweenawan in character. And the paleomagnetism indicates that if you look at the green circle in the top left of the Keweenawan polar wander path, it coincides when Coachland is restored against Laurentia as that little green box labeled CL. It is quite in keeping with Coachland having been a tectonic tracer for Laurentia, little fragment that came off what we now think of as the Texas margin of Laurentia. And so it may be that we have in Coachland a tectonic tracer for Laurentia, and we're pursuing that. The fact that the Moltke Nunatax rocks are much more deformed suggests than the structurally overlying Bertram and Littlewood granophyres and rhyolites suggest that they may be a basement to these 1.1 billion year old, possibly Keweenawan rocks, and work that absolute neodymium isotopes that Stacy has done suggests that they are very much like the basement of the Franklin Mountains and other localities out in West Texas. And this is something we have a proposal into NSF to do more geochemistry and geochronology on these rocks. Particularly now we have these very small samples that the Indians brought back. You can hardly blame them for being small. Then they had to climb up a rope ladder back into the helicopter. So what must have happened, if this is all correct, just for the Western Laurentia, the part of East Antarctic Australia that would have been in contact with it would have been what's called the Mawson Craton. That's because when we did the original work back in the 90s, we didn't really take into account the Pan-African late Neoproterozoic to earliest Paleozoic sutures that there are beneath East Antarctica. We know they're there. We don't know exactly where they go. Certainly there's one through the Shackleton Range, but the hypothesis would be that the Mawson Craton, the part of East Antarctica, Australia, that was directly against Laurentia, would have had to swing round in a counterclockwise sense there to collide with Kalahari in the Grenvillian, with where the Grenvillian origin is between Laurentia and Kalahari, to collide in a Pan-African suture through the Shackleton Range in Antarctica. And this map by Rodriguez Martinez and others, which was fairly recently published, shows where in the little blobs of bright turquoise colors there are along the Transantarctic Mountains and in Eastern Australia, and in the Shackleton Range south of the Mozambique Sea, there are archaeocyathid reefs, the earliest reefs, apart from stromatolite reefs, the earliest Phanerozoic reefs, and that shows the continuation of the Mozambique ocean there, where Kalahari and the Maud Belt would have collided with East Antarctica along the Shackleton Range. And so the continuation of the Yavapai Mazatzal of southwestern US into the Shackleton Range of Antarctica is complicated by the fact that the Shackleton Range has this Pan-African latest Neoproterozoic to early Mesozoic, to early Paleozoic suture. And on the right-hand side there's a picture of the Heimefront shear zone, which is one of these Pan-African shear zones, reflecting the collision of Kalahari Maud Belt with along a Pan-African suture in that area. Very briefly, I'm not going to try to get into the details of these, but the detrital zircons have come into their own in recent years. There have been suggestions that zircons, Medig and others, show zircons from the Mount Isa inlier having finished up in the Coal Creek inlier of the Yukon. Stewart and others show Victoria Land rocks, detrital zircon finishing up in the belt supergroup of Western North America. On the other hand, Mulder and others suggest that zircons from the southwestern US have finished up in Tasmania, even. And there's very strong correlation between the detrital zircon ages of the Vishnu Basin, as it's called, from the Grand Canyon area of southwestern US with the Shackleton Range igneous rocks of 2.4 and roughly 1.6 to 1.8 billion years. Again, the Shackleton Range having apparently a correlation with the southwestern US, as Eldridge Moore had suggested. On the other hand, Rapella and others have found what seem to be granite rhyolite province zircons in the Mara block of South America, using not only the age of the zircons, but hafnium isotopes as well. Large igneous provinces come into their own, particularly in trying to understand the northern margin of Laurentia, present northern margin. There is, as Ernst and his colleagues have shown, a very strong correlation between the sort of barcode, as they call it, of the igneous rocks of Laurentia and Siberia, most particularly that of the Mackenzie swarm, dike swarm, and the it's equivalent in Siberia, strongly suggesting that there's a long-standing correlation between Siberia and northern Laurentia, reaching into about 700 million years, the time of the Mackenzie swarm. So to sum up the story then, we have Laurentia here shown with the suggestion that I had of the Caledonian Appalachian or Scottish promontory of Laurentia, perhaps coming out of the Arica embayment. But Laurentia sandwiched between Western Gondwanaland, South America, Africa, on the one hand, and the Mawson Craton of East Antarctica, Australia, on the other, with Siberia to the north and the Coatsland, Namaqua, Natal, Maud Belt, and Kalahari to the south, and these different zircon paths, which of course are open to a lot of interpretation as to exactly what drainage systems were involved. It's a complicated story. And I just put in the bottom right there to, I've used the Mojave potential connection with the Pensacola embayment in Antarctica, which allows the Wernicke breccias and the Olympic Dam deposits of Yukon and Southeast Australia to be juxtaposed with each other. But I put John Goodge's reconstruction there just to show that there is an alternative here, and it's a little difficult to reconcile. As I said, the very strong correlation of the clasts in the moraines of transantarctic mountains with the granite rhyolite province on the one hand, with the apparent lack of continuation of the Grenville province. One possibility is that since all the clasts that looked like granite rhyolite material in the transantarctic mountains are just that, they're clasts and moraines. They may have not come from exactly where they are found, close to where they're found today, despite the fact that John Goodge and his colleagues did a very careful job of tracking the likely path that the ice would have taken and tracking back to where these rocks should have come from. So there's a conundrum there between difficulty in reconciling these two aspects of these two reconstructions of Western Laurentia against East Antarctica, Australia, and Kalahari mod belts. And I just shown the other possibility for for the Appalachian Caledonian margin, which is that it was up at the Scottish Caledonian Appalachian promontory was more between Amazonia and Baltica than down out that came out of the Arica embayment. It was always my pet hypothesis that the Arequipa Massif of southern Peru was a bit of Laurentia, but in her dissertation with Jim Connolly in the department, Stacey Lloyd proved me wrong. And so a favorite hypothesis bit the dust there. I mentioned at the very beginning that one thing you have to reconcile with for any reconstruction of Rodinia is how it got to be where it is. We know it was within Pangaea. We know where it was because we have the seafloor spreading data. So we have to get it up, so to speak, up north in present day terms in order to collide with Pangaea and to take its position within Pangaea. The strongest piece of evidence that it moved up that margin is the presence in the Argentine pre-Cordillera, seen from a Russian space station photograph there, of rocks like Northwest Scotland with the Laurentian fauna, the Ollinellan fauna, the benthic trilobites, which are only known in Laurentia, Northwest Scotland, and the Argentine pre-Cordillera, as with Saltarella, and another strange little fossil that's only found in those three places. And with Scotland, we know it was originally a piece of Laurentia. It only rifted off 55 million years ago. We can trace the tram lines that it traveled on, getting it away from Laurentia. For the pre-Cordillera, we can't do that because it was docked it was docked within Gondwanland by the end of the Ordovician. We know that because it's glaciated, whereas Laurentia is not. So it had to have been part of Gondwanland by the Ordovician. So we don't have a seafloor spreading track for it. Either it collided with Laurentia and was transferred to Gondwanland in the same way that Italy was transferred to the Adriatic promontory of Africa was transferred as Italy and the floor of the Adriatic Sea to Europe during the Africa-Europe collision, or as most people prefer, I'm in the minority here, with our colleague Pat Dickerson from the department, in thinking that it was actually still attached to Laurentia when it collided, when it docked with Amazonia and got broken off. Pat now has zircons from that look identical. They are certainly identical in age. And she's doing more geochemistry with Mark Fanning on these now. Zircons in West Texas in the Ordovician that are identical apparently to those in the Famitinian belt of Argentina, an island arc of mid-Ordovician age. And they may have been carried, as you see in that reconstruction, using the paleomagnetic data with the well-established position of Laurentia across the equator, at that time running from Greenland and Hudson's Bay down into West Texas. They could have been carried to West Texas by the southeast trade winds, which are shown by the little arrows there. And but regardless, the presence of the pre-Cordillera as a piece of Laurentia, whether it collided with Laurentia or whether it was moved as a little microcontinent, it couldn't have been far away when you look at considerations of the speed with which it would have had to move from drifting from Laurentia in the late Cambrian to docking in Gondwana land before the end of the Ordovician. Just for fun, since I was reading today about Idalia, the hurricane which was headed towards my son's house in Florida, but I'm glad to say missed. I was reading in CNN about the new hurricanes getting further inland. And just for fun, I put in the track of the hurricanes that we believe hit the Baraboo quartzite in Wisconsin in the late Cambrian and Ordovician. There's that red track across Laurentia. There's strong evidence that my colleague Bob Dott, the late Bob Dott from Wisconsin, dug out from the size of quartzite clasts that are rounded in the southern part of the Baraboo ranges, that there must have been tropical storms, hurricanes traveling across the North American shelf and continent 2,000 kilometers from the sea during the late Cambrian and early Ordovician. At a time when, remember, there was no ice on Earth except maybe the highest mountains. It was a greenhouse Earth at that time. So this may be a somewhat more extreme version of what we're looking at today, but that's a digression. Big digression. And so I leave you with that this is written up in the volume that's just coming out it's available online in a volume in the London Geological on supercontinents, orogenesis and magmatism in honor of Brendan Murphy in Nova Scotia. And just leave you with these question marks. I think you can make a strong case for saying that Laurentia was the key to perhaps the core of Rodinia. Rodinia may not have contained such a high proportion of continental crust on Earth as Pangaea did. It looks like there were other bits floating off on the ground about, but this may well have been the core of Rodinia. And to continue the metaphor, I might just say that it looks like to me very strongly as if Laurentia may have been the key, but we don't quite know the shape of the lock yet, exactly how it fitted. Thank you very much. Sorry, I overwent my time.
We have time for a few questions.
Yeah, I've got a question about, you mentioned this floating fragments. I was going to ask, in this setup, where is India? Where's the North China block? Where's parts of Siberia, etc.?
Still being argued about. Yeah. And if you go to papers like the one by the recent models, you'll find them. You find ideas of where they are, but they're largely based on paleomagnetism.
Mm.
Yeah. Yes, sir.
So, how do you get like the sort of shape of the western margin of Western North America? Because I think you showed like a paper that came out this year that had some kind of lines drawn, and I was just at a conference looking at that and then applying that. affects like recent sort of late Cretaceous tectonics of North America. It seemed that the lines were in different places. Yeah, this one here.
Yeah,
So
well, it's,
like how well known is that? And yeah,
they still have a Mojave sticking out there. Which were you referring to particularly?
so it was on GSA Penrose, and there's this model by Basil Tickle called the Hit and Run model, where they have Baja, British Columbia, like all of the sort of terrains in Canada sliding up
Oh,
and hitting a bit in Idaho that sticks out. And
right.
on this map, there's nothing really sticking out. So it's like, you know, if you go on different maps, then this whole idea is sort of
Yeah.
different. So that's something how they get them.
I think that's next generation.
Okay.
Look at it in more detail. And I'm not quite getting, you're suggesting that you're another promontory up there that,
So yeah, they had
Yeah.
a promontory in Idaho
yeah,
in their model.
okay,
So
yeah. That would be against part of it, in my preferred model, it would be somewhere up in Queensland. So I don't think we really know that the Tasman line well enough to be able to find that. But I haven't tried to fit that exactly.
Are there any questions online? One more? Okay, last one.
No one else has a question. I have another question. How do you account for continental material or continental fragments that might have been destroyed or that we don't have a good record of today? Like I'm thinking about during the India-Eurasia collision, like all of Greater India is shoved underneath Eurasia
That's a
and
good
gone.
question. Yeah.
You know, so are there kind of gaping holes in this puzzle that could be, you know,
Well, one can argue as well that you may have lost part of Western South America to subduction erosion, which is not very different from what you're talking about. Well, there are just uncertainties that have to be acknowledged. And I suppose if you came up with some particularly strong piece of evidence, you might be able to argue that something was lost. I haven't come across anything like that I'd want to argue has disappeared down a hole.
yeah,
But,
you have to know it exists
yeah.
for you.
Right.
Okay.
Well, let's thank Ian one more time.
Thanks for coming.
Next week, we'll be hearing from Sarah Seaberth here at UTIG about projects going on at UTIG and also Malcolm Ross at the BEG, talking about a research symposium going on there. So yeah, see you all next week here again at 2 p.m. Thank you.
Thank you.